Hello students, in this video we'll show that our construction of Brownian motions converges almost surely to a continuous function. Let's recall what our construction does. I let xc0, xc1, xcn be IID normal 0, 1, IID normal 0, 1. And then we set bt to be xc0 t over root pi. That's no problem continuous. That's just a linear function in t, right? The continuity of this thing is non-question. Plus the square root of 2 over pi. That constant won't affect my continuity at all. Then I'm going to say n goes from 1 to infinity. Then we have this random series, xcn, then the sine of t and t over n, right? And that's where the real issue lies, right? And so there's a classic results on random series of how we approach solving these things. And so the best approach to do these things is to break up this into dyadic blocks and estimate the dyadic blocks, right? So I'm going to define Qn of t, just as the sum. I'm going to forget about the 2 over pi. That constant won't affect my continuity at all. I'm just going to look at the sum. K goes from 2 to the n minus 1. So when n's equal to 1, this is going to start at 1 up to 2 to the n minus 1. So I'm going to go from 1 to 1 for the first one. So the Q1 is just going to be from 1 to 1. Then the Q2 is going to go from what? It's going to go from 2 to 3. Then it's going to go from 4 to 7. So these are perfect dyadic blocks. So in other words, if I sum up all these Qn's over here, I should get my original series. So I'm going to have xck, the coefficients over here, and then the sine of kt over k, like that. Okay, excellent. And so now Q is a trigonometric polynomial of degree n. And so the beautiful thing about this, I get a cheap L infinity estimate from this. And so the idea now is that for any, so if, just as a quick lemma, if P is a trigonometric polynomial of degree m, then the L infinity norm of P can be controlled by the any P norm we want, right, or any Q norm, whatever we want. So let's say this is less than or equal to what? I'm going to say, let's call this, I'm going to change this P to a phi. Okay? If phi is a trigonometric polynomial of degree m, then the L infinity norm of phi, I'll put P norms over here, is controlled by m to the 1 over P, the degree to the 1 over P, times the LP norm of phi. Okay, so in other words, for a finite dimensional, on a finite measure space, I know the P norm is the L infinity norm controls the P norm, but vice versa is true for trigonometric polynomials. And the proof of this is actually really simple. All I got to just know is that phi, here's the proof. Proof is that phi, since it's degree m, is just going to be the Dirichlet kernel m convolution with phi. It's self-convolution. I'll take the L infinity norm of this. So this is the L infinity norm of phi is actually equal to the L infinity norm, which by Young's inequality is less than or equal to what? Less than or equal to dm in the dual space. So in the dual space, and then the LP, right? So let's use Young's inequality for convolutions. Okay, and I know that this is comparable to what? The Q norm of the, we proved in a previous video that when P is strictly bigger than 1, right, and not infinity, that this is exactly equal to just m to the 1 over P, right? That's in the previous video. We can link to that. Like that, we get our estimate for free. Excellent. Okay, so that's great. So now this allows me, this allows me to estimate the P norm over here, and then I can control the L infinity norm, which is what I want, my uniform estimates on this thing over here. So what can I say over here? Now I'm going to compute the expected value of Qn to the 4th power. Okay, I like even powers, and 2 is not quite enough to get me what I want. So I'm going to look at the norm of Qn, the 4 norm of this thing, and I'm going to compute the expected value of the 4 norm of this guy over here. Okay. All right, excellent. So my P is equal to 4 in this case, right? All right. So what will this be? This is going to be the expected value. Now, remember what's going to happen when I raise everything to the 4th. I'm just going to raise everything to the 4th power over here. The expected value, 1 over 2 pi, the integral from negative pi to pi of this whole sum over here, the whole sum, k goes from 2 to n minus 1 to 2 to the n minus 1, xck, sine of n k over k to the what? to the 4th power dt. Like that. Excellent. Yikes. There's lots of terms to unpack over here, but let's think carefully what we're going to get when we do something to the 4th power. When we do something to the 4th power, what terms are we going to get? We're going to get pure powers over here. We're going to get xck to the 4th power. We're going to get xck squared, xcl squared. We'll have terms like xck, xcl cubed, like that. And then we'll have terms like all of them different. So we'll have xcl, xcj, xck, xcm, right? And then all of the terms that have one odd parity are going to vanish by the fact that they're independent of each other, right? So the odd parity terms vanish, so odd parity vanish by independence. Okay, so really there's only 2 of these terms I have to compute, right? And so now I'm going to start to do things up to constants, right? Because there's going to be constants flowing around everywhere, right? Just remember that involves pi. So let's look at the terms that we're going to get. We're going to have 4th moments, so we're going to have 1 over 2 pi, negative pi to pi. The sum, k, goes from 2 to the negative n to 2 to the n minus 1. And then we're going to have these numbers over here, sine of k. And of course, the 4th moment of xck is, I think, 3, right? So that's where you're going to start pulling out like a 3. That's for the 4th moment. 4th moment. Okay, k over k to the power 4 dt. Those are some terms we're going to have. And then I'm not going to be able to figure out the exact count of these things. I'm just going to say rough on what order do we have these things over here. So on order what? Then we have some constant plus some constant c, integral from negative pi to pi. Then we have pure second moments. Then we're going to have the sum over k and j, k not equal to j, going from 2 to the n minus 1 up to 2 to the n minus 1. Then I have just the moments, then we have these things squared over here. So we're going to have a what? We're going to have a sine of kt over k, and then the sine of jt over j squared dt. And so now let's just count the overall expected value over here. So what we're going to have over here. So these things look like the sign is bounded by 1. These are k to the power 4. So k is in the order 2 to the n. So these are going to be adding k to the what? That's going to give me these first terms over here. So this is less than or equal to a constant 2 to the negative what? 2 to the negative n over 4. Negative n over 4. Negative 4n rather. Negative 4n. Right? Because I have n to the 4th power over here. And then there's 2 to the n of these things, right? Times 2 to the n of those terms. Plus a constant over here times what? Plus a constant times, these things are all in the order 2 to the power negative 4n. And then I have how many of them? I roughly have 2 to the power n squared of them, right? Or just 2 to the power n. So I'm going to have a what? That will give me 2 of those things, right? So that's going to be a 2 to the power negative 2n, right? For the just positive 2n, for the number of possible pairs. I can probably do a little bit better than that, but that's all I care about. This is the rough estimate I need. So on order, what have we just proven over here? So the overall order of this is like a constant times 2 to the negative n over negative 2 to negative 2n, right? So we've just shown that the expected value of qn to the 4th power is on what order? Is less than or equal to, of course, c times what? C times 2 to the power negative 2n, like so. Okay, good. Now, of course, what's the relationship between powers over here? Well, I know automatically that the, if I raise things by Jensen's inequality, this is bigger than or equal to, by Jensen, qn to the 4th power to the 4th, because the 4th power is a convex function. So this is just Jensen's inequality. Jensen's inequality. Okay. But now, what can I say? So now I can say, therefore, I can combine. Now I'm going to use this bound over here. Okay, so what's my L infinity bound? My L infinity bound is this. So this implies that the L infinity bound, the expected value of Qn in L infinity, is less than or equal to. Well, it's going to give me a 2 to the what power? So I have a 2 to the n to the 1 over 4. So it's going to be my error factor is going to be a 2 to the n over 4, to the n over 4. And then times the 1/4 power of this thing. So then times a constant times what? Times 2 to the, I have to do this thing to the 1/4 power over here. So raising it to the 1/4 is going to give me a n over 2, negative n over 2. So this is a negative n over 4. So this is a constant times 2 to the negative n over 4. So now I have this estimate on the expected value of the Q norm in L infinity. Now we're going to use the Chebyshev inequality. So by Chebyshev, what do we get? So by Chebyshev, I know that the probability that Qn in L infinity is bigger than or equal to. Now I need to squeeze this down a little bit. 2 to the negative n over 8, right? Is less than or equal to what? Is less than or equal to the expected value of this thing, which is a constant times 2 to the negative n over 4 over 2 to the negative n over 8. And that's just going to be a what? That's going to be a constant times 2 to the negative n over 8. So this is just a constant times 2 to the negative n over 8, right? And now we're done because this expression over here is summable, right? So now, since the sum n goes from 1 to infinity, the probability that Qn in L infinity, of course, in L infinity is bigger than or equal to 2 to the negative n over 8, right? Is what? Is summable, is less than infinity. So by Borel-Cantelli, the complement of this happens almost surely. So by Borel-Cantelli, this says that L infinity norms Qn L infinity less than 2 to the negative n over 8 for n bigger than or equal to n naught has probability 1. And since this is a probability 1 event, I have that my series over here is uniformly controlled, is it uniformly summable, so I know that, what do we have over here? So now I can apply the Weierstrass M test. By Weierstrass M test, my BT is continuous, almost surely. Because I'm writing my BT, these terms over here are really what? I'm really summing. I can also write BT as really the sum of this continuous function plus 2 over the square root of pi times these things over here on dyadic scales are Qn, right? So I have a sum of functions who are uniformly bounded, and that uniform bound is summable, so I know by the Weierstrass M test that this B of t has to be continuous almost surely. So Brownian motion is almost surely a continuous process. Thank you very much.